Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have our lecture 5 on parallel programming with OpenMP. And OpenMP is basically the de facto standard for shared memory programming and is also something which should be not really kind of confused with OpenMPI. So many of you have used OpenMPI now in the course. We had MPI in and out in practical lectures, and this is really different. OpenMPI is an implementation of the MPI standard, while OpenMP here is really de facto standard for shared memory. And I will talk about it throughout our lecture 5 today. But before we go into the material of this lecture, let us review what we had the last time. And the last time was really one of a pleasure for me because we have an invited industry partner, Rescale, teaming up with the Borealis data centers in Iceland, and did a teaching, if you remember, that we called Practical Lecture 4.3, which was really an application of OpenFOAM and then using this Rescale platform. So you have seen that essentially HPC is possible to, so to speak, put it in a cloud or abstract the complexity via a platform. And many of you are now solving the assignment around it. So, I mean, many of you know that this is quite a nice tool. You sort of abstract from the job scripts that we had in earlier lectures, especially around MPI. But you also have seen that there were many application supports in this Rescale platform. And this is really a benefit that you have with these platforms. They support a lot of application domains, not only the computation fluid dynamics that we have seen in the last lecture here with the OpenFOAM solver, but also many other tools and even AI, as I was asking the last time. So this was really combining then the efforts we had with MPI in the beginning, a couple of lectures before, bringing us to 4.2, talking about OpenFOAM and open source solver of CFD, where you can where you can use to solve interesting questions around it. And you see some of them are definitively about the motorbike we have done in the last lecture really on our own, or almost all of you had an account on Rescale and could actually benefit from this. But of course, there are also larger experiments that you can do, like an airplane here, for example. So I'm very grateful to the team you see here, Mark Fieldhouse and Romain and all the others, Christian here, Reza, bringing that up to speed, this lecture. And we have a collaboration with Iceland, a lot with Rescale, hopefully in the future. So just to connect it to HPC, the things you've seen, which was not completely obvious to you because it abstracts a lot, was still running in parallel, right? You saw that here. For instance, 18 cores as an example was running somewhere on some HPC system you don't see, because this is abstracted nicely from the Rescale platform. And this is one of the, let's say, unique selling propositions of these platforms. Of course, let's not forget they come with a cost, but of course the cost stands for that you don't have to worry about all the details in the job scripts, especially if you think about that you operate on maybe 20 HPC resources worldwide. You always have to have different modules, different elements, etc. And here the Rescale platform really helps you to abstract from this and can just use the OpenFOAM solver here, for example, to really solve your numerical problem that you have for a specific situation. So that was really a nice lecture. I hope you liked it. It was some up-ramping to do to really get this done, especially as an industry partner is involved. But NC eHPC workshop and so on, we have also close contacts with these companies. So, however, let us come back to lecture 5 today. We are getting more and more into substance from HPC, which is of course now also clear because we're almost in the midterm. So that is something what we have to consider now, parallel programming with OpenMP. And let us then look what we want to do today. We have these two parts. The first is really thinking about, again, shared memory programming. And this is something I started the course with. If you remember, I said, well, distributed memory is MPI, shared memory is OpenMP. So in a way, we sort of now stop a little bit on this MPI and dive into different domains, which are also highly relevant for high performance computing. And today we have really shared memory. Of course, shared memory in a sense, if you remember, is a bit limited. We really need the access to the memory, hence the name suggests. So in the end, you would probably even combine distributed memory with shared memory programming. But this is not at all a whole lecture about OpenMP. This would be completely 1 week from morning till evening what you can do with OpenMP. It's a very strong standard, a very strong implementation where you have parallel serial regions. We will talk about this and also what it means to have a master and worker thread and how you can fork and join these threads and how they, of course, nicely connect to your job script, right? So this is something again, with scalability in mind, where you can steer the number of working threads also via the job script. Then we talk a little bit about the portability aspects of it. It's a standard. So, of course, OpenMP enables us, almost like the MPI standard now, to go between different systems. And there I have another OpenMP implementation I can just simply use, and my code will usually run. Now, thinking about the next, let's say, evolution of this and what has, let's say, really given input to the OpenMP standard was developments in comms and PyComms, and I will talk about it. Also thinking about a much more task-oriented and data flow-oriented evolution of this. So today we have accelerators. Some of you don't know exactly what that means. It will materialize in the next lecture when we talk about accelerators. But I will motivate a little bit the GPUs that we had already a little bit in the course in the beginning, right? You remember the many core GPUs, where now this changes the game a little bit, how you program these systems. There are even standards around with OpenEgg. I will talk about it, many others. So in the second part, we then will really look a little bit into practice of this. So what are the basic building blocks, how to create an OpenMP program. Again, C is here for us, the modus operandi, but of course there are different implementations, what you can use. And then we look at simple, let's say, elements, how you can use OpenMP. And that is by far the parallelization of loops, but also thinking about different variable types that you can share or keep as local and so on. You can imagine when I have access to a shared memory, and let's say I'm 1 out of 8 or 16 threads, there's some sort of a problem when you access several variables. We talk about this about critical regions, right? So this is a bit about synchronization, and of course, not everybody can write and read those variables at the same time that you have in shared memory. So there must be some ways to protect and synchronize these threads, and we will talk about this in the second part. And of course, then we should also contrast it a little bit to MPI, what we had before, because this is something which often students still confuse, after many lectures and in the exams and so on. When we talk about OpenMPI and MPI versus OpenMP, we will talk about performance issues. And then I have a couple of application examples just briefly in this course here to show you it's still very valuable to use shared memory. And why? Because memory is extremely fast, right? No matter if you do distributed memory programming across different nodes, and we have seen now your HPC systems like Lumi, which have many, many nodes for you, but it's still feasible and useful to exploit the shared memory in the parallelization task at hand, because this gives you an amazing speed. Although it's very limited, it's within the node. You cannot go across the nodes. You need distributed memory programming for this. Hence, normally, let's say in some application examples, usually you would combine them, MPI and OpenMP. And this is an example when we look at the clustering example I brought you here, the HPDB scan. You already know from previous lectures, but here we will make the connection now why we also use shared memory. So in a way, also a practical lecture. When you know about this, you will see that you can use OpenMP very quickly. There are just a couple of, let's say, Sentinel and then some paradigms and elements you have to use to automatically, essentially, parallelize your code. And we will dive into this. However, I have to say also from the learning outputs, in former times, we did much more on this. We did several assignment parts. I did some practical lectures. Now, given the rise of GPUs, given the rise of AI, Also, this course was more or less tuned now as a special for CFD. We had to sacrifice some of this. And in the end, you will see in the YouTube recordings a couple of years ago, we still had practical lectures that you're, of course, welcome to look at. But OpenMP will be not the main paradigm here in the course. But if you're interested, of course, as I said, in the Jülich Supercomputing Center or in many other centers around Europe, there will be lots of different courses on OpenMP, and chances are that many of them are also open. So in the Euro HPC environment of projects, we currently thinking about training portals which really open up the training resources like you as students to have OpenMP tutorials at your hand. Hence, again, this course cannot cover everything, but if you have understood the findings of this, you will definitively have another understanding of how to do complex aspects of parallel programming. And here we talk really about extremely complex, because we're going into a world where not only you do OpenMP shared memory in one node, and then with distributed memory programming with MPI across different nodes, you may even combine that with accelerators to accelerate parts of your elements of the code with GPUs, for example. So this is an added complexity, what wasn't there 10 years ago when GPUs were just for gaming, right? In some home computers to have a nice gaming experience. Now we face a much more complex aspect of parallel programming. However, the beauty is that one standard learns from another in a way. So we will learn a little bit today and basically in the second part that a little bit this will be to a future where hopefully the parallel programming gets a bit easier. So you would think about more a task way of programming. So when you come to this, of course, to tasks, you quickly end up with data and data pipelines and workloads, which are sort of, in a way, data intensive and need to scale. Hence, this is also another learning outcome to think about more of the data, obviously, and intertwined a little bit at the end, also with a new paradigm of accelerators, which we will also look in detail then in lecture 6. So in a way that you're really ready after this course to have a so-called hybrid parallel programming. You would do different types of parallel programming, MPI, for instance, combined with OpenMP. So let's dive in shared memory programming concepts. And a couple of these things will be actually something that you already know. So we'll, of course, connect to the initial parts of this course, lecture 1, where we discuss a little bit, even in the prologue, we discussed a little bit about the different programming concepts, how to do parallel programming. We focus here on shared memory, but of course, it has relationships to many other aspects in your computers, which we call then the HPC machines. Here you see the idea of the shared memory here. When I do the cursor here, you see we have the shared memory somewhere in your big HPC machine within one node. And then you would kickstart many different threads, and we will talk about it, how you do this, how they fork, how they join. But just to get the feeling now a little bit that we talk about lightweight processes, right, that access data. So reading variables, writing variables, reading variables, writing variables, and so on. So these are threads and within a node. Before in MPI, we talked much more about processes running. And then, the processes had inter-process communication really to exchange data. Here, what you can do is you basically just want to read something out of memory and write it back. Of course, it isn't that simple as you can imagine. There are different ways how you do it, and also, of course, problems with consistency, especially if you want to read and write, more notably, of course, the same variable. However, this OpenMP standard that we have comes with a different, set of options and so-called compiler directives to really help us working with this, not only to mark parallel regions, which is important, but also thinking then about the consistency and critical regions, as we call it. So in a way, think about much more lightweight ways how to program in one respect. And of course, you can see that some of the nodes we discussed also in earlier lectures had this unified memory access. So they're really having memory and all the CPUs can directly have this access to memory. But we see also in practice, that's not always true. We had this bus interconnect, if you know, with cache currency and stuff like this. But non-uniform memory access is also something which is actually known, called CC NUMA, for instance, CC again for this cache currency, and then the unified memory access. You as a user, however, will not really notice that. What you have to much more take care is exactly this programming in parallel and making loops useful in terms of parallel regions and so on. And that's what we will talk about. So think about UMA and this idea we see here. Again, think about the memory that we can have, that is really all the processors that we have this different level of hierarchies of caches and can create a direct, let's say, read and write instruction to memory. So this is quite nice. It enables us, of course, with the most performance you in a way can get if you're so close to memory. And as you know, memory is in a way really very fast, although of course the main memory suggests it's slow. But you have still this different caches here, right? And hence the memory is very fast, also going through this different level of caches that you see here. So in a way, it would be perfect just using that, because then it would be very fast. You don't need, basically this buffer that we had an MPI to send and receive and to do collective operations and so forth. However, the world is not really like this. Although this looks a little bit like distributed memory, what it is in theory, here we have this coherent link that I was explaining also earlier lectures, which is the so-called CC-NUMA architecture of shared memory, where there is a kind of single address space, which is now important. So you as a processor here, you don't really care. You still see these distributed memories as a single address space to address your variables where the variables rely, where the address is that you can gain for read and write the variables. And with this is an important factor. So you as a programmer don't really need to know this, right? Just to review again, CC NUMA and all the details. Although it's physical distributed memory, you actually program it as shared memory, and that's the point. So meaning then, or getting a meaning out of this shared address space I was just mainly actually alluding to. And as I said, it doesn't matter if it's CC NUMA or UMA. Here you see an example of the top right? It's very easy to think about. You could have one thread and another thread, and this shared data, the shared single address space, will contain your variable. Now, the interesting thing is if you have this MIA28, it will be for the thread somehow working that you say it's okay, it's my shared address space, and I do something with it. So I would say A is, for instance, like this MIA. Then I would work as a thread in this, and I have this private data, which is now 23. When another thread is working on it, it can, of course, simply just read that data and say, okay, because I know already another thread is using this and, writing this into memory, I can just simply reuse it. Like here, I know it writes A into the shared data as an example, and reusing A as thread 2, which is then 23, and add a 1. And, thread 2 can have another MIA variable for itself, having now 24. But the key message to take away is really then there is no send and receive, right? Here we directly talk about assigning variable data. We directly talk about reading A while we also write A. Now, this, of course, in your mind should directly say alarm bells, right? If you heard 101 computer science, I hope at least the most of you will have that again and again when different threads, have so-called race conditions around a variable. So here it matters now precisely which thread is actually reading and writing this data, right? And of course, this is now something we have to talk about again and again, because this would be interesting to, for instance, mark it as critical region. But this is more for you to show now what the shared address space means. We're not talking about making a buffer, then using this buffer for send, creating a receive buffer to receive from another process, a quite complicated process, still scalable as we have seen in MPI. Here in OpenMP, we really address then the shared space. And this, of course, gives us some benefits. Of course, the code in a way is easier. You have so-called compiler directives where OpenMP is really standing for, and it instruments your code, as we say. You basically have to have some parallel elements in it, which you usually have to serial, and then you mark it with a sentinel, the OpenMP sentinel as a parallel part, and then you have to modify this parallel part, whatever you want to do with it, right? So there's a statement, of course, where you can now do lots of fine-tuning what OpenMP is doing. But this is an interesting element of this OpenMP standard. And then in a way, you use this as a work sharing idea. So you have different threads. Of course, you still want to have a problem solved in a, let's say, collaborative way. But now you don't do this with sending things over the network, but rather do the shared address space and then, using the data that is within the space to do some work sharing. And of course, loops, for instance, if you can think about it, and many others would be quite an interesting way to do it. However, how we do it will be now something what we have to talk about, how we actually basically spawn threads. Spawn threads is something which is a very important term you have to understand, because it's these kind of ideas that you can spawn them, and then at some point in time you maybe don't need them, so you stop them again, and so on. So in a way, this is the benefit of all of this, because you have a sort of lightweight approach to this parallel programming. So with modifying this number of threads, which is now important differentiation to MPI, where we say rather process, this is an important part. And I brought you here some quite nice overview in terms of visualization, how that works. I think that should show you a little bit that you have an OpenMP program that will be shown in code later, where you start maybe with a sequential part, then you have a parallel region, then you need somehow a sequential part again, right? Think about the divide and conquer maybe as one of the examples I had in earlier lectures. And after the sequential part, then you have another parallel region where you maybe want to have some summary statistics, and then the sequential start again. So in other words, you would have this master thread, which is your program. Let's say it could be rank 0 that you know already from the MPI jargon, but here we don't really talk about ranks, right? Here we have a different way of handling this. We call that threads. And you see, however, we have still a way of determining how many threads are in the parallel region, almost like you know already from MPI. So we have parallel regions here that we can fork at some point in time and then join again to do this serial region or sequential part, really, as we discussed. At some point in time, then we think, okay, it makes sense to, again, spawn a team of threads, which might be not the same number, and because the work might be lower or whatever. That is something to think about. So hence the OpenMP standard gives us really a broad standard with lots of directives that we can use. And here what you see already a little bit alluding is then here the OpenMP runtime and how it works. So you would have basically this parallel program as a normal C program, or for some of you that are inclined still in Fortran, you have seen at the EHPC workshop people using still Fortran. So here you see the Sentinel Pragna OMP parallel, then actually marking a certain part of your C program into parallel to mark a parallel region. In Fortran, you would say omp and end, basically here. So you start a parallel region and end it explicitly. In C, you have the brackets. But in a way, that's really now the details. The key message really to take away is this parallel regions versus this master thread, who basically as a thread then automatically become part of the parallel region, actually, so to speak, thread 0, right? That actually then, once the parallel region collapses or joins as we talk, will continue in the serial region. So here we have this sort of master worker paradigm really in effective action. Another visualization of this so that you understand that perhaps a bit as a sort of lifeline, right? So you have to, the master thread always exists, which is a lifeline of your computing in your program. And then you as a programmer have now to understand and see in the parallel regions how many threads you want to fork. And then, of course, at some point in time, they probably join again. And this join might be not always very explicitly. You see here, Pragma OMP as an example, Fred and Billy will be then in parallel, and Daisy again, basically then in serial, right? Like the view here suggests. But the point is really, you as a programmer steer this parallel region. And the team of threads could then do this particular operation much more effectively. But this means also that in this example, Billy somehow, this operation or function should be making use of these threads, right? So this is also another part, because now this will be executed by different threads. We have to understand that, of course, now this function should be somehow leveraging these different threads. So in one respect, it's very easy to understand this parallel part, and especially then serial versus parallel regions, right? So that's, I think, the lifeline you see here below. But of course, when it comes to programming, it's not that completely simple, especially if you think about, again, the race conditions around variables, but also the project logic that you want to do. So you want to do some scientific applications. Left alone, of course, what happens if you do hybrid programming, so combining this with MPI. So thinking about the OpenMP standard, that's a slide you almost a little bit can compare to the MPI standard. Again, you as a practical programmer, when you are coming out of the university maybe and then begin your career, you will have access in the HPC engineering space maybe to 5 to 10 systems. And they're not at all same, right? So there would be a Cray system there, an Evident Atos system there. There will be maybe still other systems around, older systems, EBM systems. So in the end, what I want to convey is your systems will be always looking a little bit different. And this has been to do with many things. It could be 4 nodes of GPUs, or let's say more accurately, 4 GPUs within a node, or 8 GPUs within a node, what we see also in the HPC landscape these days. It could be a Hopper GPU of this type versus maybe an A100 in others. So you have different technologies, you have different number of RAM cores, GPUs, and so on available. However, the beauty is in this OpenMP standard, very similar like MPI, is then you can sort of assume when you have another HPC machine and it has an implementation of OpenMP, it will run. There might be some smaller modifications to this. And of course, here I also alluded to the idea that, of course, with accelerators, we are very close to have a sort of portability with OpenEgg and other things, which are very close to the OpenMP standard. But when it comes to the complete new HPC systems, like the D-Wave Quantum Annealer here, we're doing actually a lot of research around that in my research group. That is, of course, not at all that trivial. So it has its, let's say, limits. Think about the HPC machines, which are, so to speak, more in production today and not really research vehicles like our quantum devices. Still, the low level of that is, of course, still something you have to think about. So how much memory is there really? How many RAM I can allocate for my applications? An important factor if you do shared memory programming, because this will determine how much data you can store, how much you can really quickly get in and out of this memory. Hence, the portability is an important factor. And then when you want to scale, and now comes really the idea of having beautiful code, which is not at all that simple to program. So when we talked about, and we had this already in the beginning, we would say, there's no problem doing here maybe shared memory programming. That's why we call it a bit like hierarchical hybrid power computers these days, right? It's not really a distributed memory pure type and not really a pure shared memory type. So what you want to do is maybe do shared memory programming within the node and then use MPI across the node in order to access also these memory spaces that you have here. So in this sense, getting bigger, bolder in terms of scalability. You can add more and more nodes. We have really very many nodes in the Euro HPC machines I was already showing you. But you would still maybe combine that leveraging the real fast pace that you can get out by using shared memory programming within the node, especially if this memory is quite rich and quite much. Another way how to see that is really here. You see that here in the OpenMP sort of way. I have one, thread living in a process, going through the cache hierarchies, writing to memory, while another is then using, the shared memory again to read it into another, let's say, thread being handled by another process. But this is something where MPI would make no sense, right? So here using MPI would mean exactly what you see a little bit alluding to. You would copy the data in a sense, and then copy the memory location in another copy to then get it back to the processor working or the thread. In other words, you see this kind of buffer mechanism that I was alluding to in earlier lectures already and demonstrated to you a lot on MPI. So we can forget about this in shared memory techniques because they can read and write the memory on the same node. And that's beautiful. And you see here some praise tutorials on OpenMP and MPI. I just give you this. We are, as I said, in the Euro HPC joint undertaking now, thinking about how we can do similar training portals. There's a development process around this. So the training portals of praise and the tutorials there will be also hopefully joined to some extent, but you will still find lots of interesting tutorials around it, because also this course in the past had one lecture about hybrid systems, but then we also, for the sake of accelerator programming and focus, we had to let go of some of the lectures. So in this sense, I would encourage you to look at the praise tutorials, or as I said, also the EuroCC and EuroHPC tutorials, which are coming along. In EuroCC Access, for instance, you would probably also find some OpenMP lectures. And if you are in doubt and want to have more, of course, you can also contact me. Hence, looking a little bit now how that should be working in practice, you would have, of course, MPI is this kind of inter-process communication where you then go really, as we discussed, from one process to another, different memory spaces, while then OpenMP and the idea of parallel programming with shared memory is really then the idea of accessing and reading the same variables. So this brings us also to the point of some stencil methods where you have a certain pattern to do parallel programming. And exactly there's also a point where this becomes quite complex because you integrate it in the application domains. And you can imagine the stencil was this idea of sending data with halo regions, for instance, in the next time step to compute. This needs to now combined with shared memories, that all data is there when you do shared memory programming, and then across the nodes you have to make sure to exchange this. So here and there other challenges like the mapping problem exist as well. But let's talk a little bit about how we would programming this. And you see that a little bit here, alluding to what was I saying before. You would essentially see the space of open memory programming within the node, very close to the memory, and meaning directly access and write and read to memory, and then of course MPI across the node. So I start off, sort of repeating myself, but I think the illustrations that you have here and the explanations is very important to understand that they're also working on different levels. And to bring you some scientific application examples where we really use this, an application example you in fact already know, right? From before, we said MPI was something we was looking first when we talked about things like speed up. So we add the number of cores, and with this we got some quite nice speed up. Here you see the linear line that we not completely achieved, but we have seen with the MPI that essentially it scales quite well. After some point in time, however, we have this tail off. And the interesting thing is, of course, it has relationships to different data sets, data set 1, data set 2. But in this particular example, I want to highlight what happens if you have, for instance, data set 1, which is, I think, one of these Bremen ones here. We also had in earlier lectures, right, to reconstruct buildings from point clouds, what we have seen by clustering. So details are not here for this particular course. It's a Davis-Scan algorithm that is quite known. But important is to realize that by combining the shared memory aspect, hybrid, as it is used to see, with MPI, so to speak, OpenMP and MPI stand here for hybrid, we could get a much less tail-off. We don't achieve linear performance, and it's still close to linear and still being able to scale up. And this has something to do with the fact that we can do, let's say, a sort of local clustering within the node and then share that with across the node MPI, as I was just alluding to, exactly in this particular application. The details of this are, of course, documented here in this paper from one of my former PhD students, Markus Götz. And you see here a little bit how that works when you now think about how we instruct then OpenMP. The way how we do this is a bit here alluding to OMP number of threads for, while we have, of course, here also the ideas of MPI. This is a batch script, from another system, not the Alias system, but it doesn't matter. But in the way you see that in order to do this with OpenMP, to combine it with MPI, you would have information in the job script, which is also something you communicate to the application. And this is something what the second part today will be basically about. So how we do this, how we work with different threads, how we want to essentially see this. At the end of this lecture, I just wanted to let you understand how these things now are, let's say, a bit progressing towards accelerators. All of you not really maybe know what the many core systems are completely about it. We have discussed it about the host memory, the device memory, and many cores which are, let's say, of moderate performance, not high single thread performance like CPUs, but rather moderate. So not that fast, but that's why it means they don't get very hot and you can put many on the chip. So you have a sort of high throughput machinery that you have there, still with the drawback that you always have to go via the host memory to the device memory. And in a way, we have seen with GPUs when we thought about the arrays we discussed earlier, and lecture 6 will then really go much more in details on this. But we have seen that essentially it's about many tasks I want to do. Hence, now the tasks have sort of an overlap to the ideas we do with OpenMP, because there's also a sort of really task-oriented view on things, how we do this with parallel regions. Hence, our programming constructs underway, like OMS here, for instance, which is a sort of more innovative way how to program, abstracting again from the lower level devices, but thinking about much more tasks perspective on parallelization, combined maybe also a little bit with a data flow experience. And you can see that a little bit how that is evolving over time, how the OpenMP standard here is really also informed by OMS, and then elements what you have here of tasks are, for instance, really integrated into the OpenMP standard over the years, which was one of the achievements of DEEP, but then also of successive EU projects. And in a way, you see also the evolution that when you do this with OpenMP and maybe with shared memory and normal traditional CPUs, you can think about similar tasks now also when you have the device memory. You see here statement pragma OMP target device CUDA. In other words, an NVIDIA GPU where you upload a sort of CUDA kernel that then should be computed on together with a couple of variables. Of course, copy out here, you understand again the idea that you have to put that first, copy in other words, from the host memory to the device memory, and then the device memory will be filled and you have to get the answer out into the host memory to further work on it. This will be something we discuss in lecture 6 much more. And in the sake of the time, I cannot go in all the details of OMS. I think that would take another 3 days just from morning till end to have you teached about a very powerful programming model, which is really quite often, or let's say more used today than in the past, and really augmenting the OpenMP standard with lots of interesting things, because here you see, for instance, what many of these HPC applications look like. There's a sort of a tree of dependencies of tasks, right? When you look into the source code, you have then several parallel regions where you do something with. The details are here not important, but important is to understand that you have, let's say, different elements like trees, or as you see here, also different parts which form sort of different dependencies on all the different elements. So having this parallelization, a little bit more task-oriented, is really an idea of this OMS programming model. And it has really the idea to do this in a standard fashion, building on the OpenMP in a way, and then also influencing the OpenMP finally when it comes to this task constructs over time. So with the success of COMS is, of course, also derivatives like PyCOMS, which is a Python binding then of COMS. And I encourage you to read this up a little bit. And the key message I want to take you on the, I want to leave you on the table here really is think about there are not really limits. And if you are more reading and writing about tasks, in some respect, you're thinking about more the data flow, the tasks on it. And in another aspect, you would say, I don't even care about where it's running anymore, as long as these tasks are executed. You can see it a little bit almost like the Rescale platform, right? We were computing OpenFOAM. We didn't really know where exactly. So here in COMS, it's the same way. You can actually have a couple of parts from the API, programming, done everything, and then you execute parts maybe on a your HPC machine, but also other parts maybe on an Amazon cloud. So here, this kind of tree-based or this task-based approach, so to speak, enables us to think broader, to think also, could we leverage, let's say, different platforms and so on, and which is really then, I think, an important part about the future, especially if you have domain-specific scientists that maybe don't even want to know what's happening underneath. I gave you here an example of OpenMP ocean waves simulation, which is alluding a little bit to the CFD focus of the course. But of course, later in the course, Razor will discuss with you some of the application packages and applications, which then also leverage again OpenMP and MPI. And that's all for this first part. See you next time.